hand you over not only to the chair for this session, but also to the chair for the next Lepton Photon conference. Ulrich, take it away.
Well, thank you, Marco. Yes, an honor to be able to moderate here on the last day. So welcome here to the last day of Lepton Photon. We will start out with a session in the astrophysics direction first, with gravitational waves and multi-messenger observations, and then we'll move on to short presentations from the poster prize winners as well. So let me first welcome Patricia Schmidt, that will talk to us about gravitational waves. So please go ahead, Patricia.
Wonderful, thank you very much. I hope you can see the slides.
Yes, all good. Just take it to full page if you can.
Yes, just have
yes, all good.
Famous panel. Wonderful. Okay, brilliant. Thank you. Are you going to give me a warning? Or?
Yes, I'll give you a warning about 5 minutes before.
Okay, perfect. Thank you very much. Well, thanks to the organizers for the invitation of this talk, and thanks to you this morning for being here with me. And it's my pleasure to talk to you about gravitational wave observations by the LIGO, Virgo, and CAGRA collaboration that we have made to date. So let's get started straight away. Gravitational waves, I think most people today know that already, are small perturbations in the fabric of space-time, and they're caused by what we would refer to as really cataclysmic astrophysical events, such as the collisions of black holes and neutron stars, which will also be the focus of this talk. And such events create gravitational waves in a frequency range of about a few hertz to a few kilohertz. And we have observatories on ground distributed across the globe, which are susceptible to measuring these very, very tiny perturbations in the fabric of space-time. Concretely, we're talking here about kilometer scale interferometers, so very different, obviously, to standard electromagnetic observatories, where you use optical instruments. So we have Michelson interferometers, very, very sophisticated Michelson interferometers that have arm lengths between 3 and 4 kilometers for the current generation of operating detectors. The main detectors we have at the moment are the 2 LIGO detectors in Hanford and Livingston in the United States, which have arm lengths of 4 kilometers. And then in Europe, we have the Virgo detector in Italy, just outside Pisa, with arm lengths of 3 kilometers. Since, and that's actually a little typo, 2021, we also have a detector operating in Japan, in a place that you all, as particle physicists, are very familiar with. It's actually located in the Kamioka mine, and is the CAGRA detector, which is also 3 kilometers long, and is still in the process of reaching a sensitivity that is comparable to the LIGO and Virgo detectors. There's also a smaller scale detector, GS600, which, as the name suggests, has 600 meter long arm lengths, located outside Hannover in Germany. And then hopefully in the near future, we will also have detectors in India, and maybe also in other places around the globe. Now, why do we want a detector network rather than just having one? Well, the simultaneous detection of a gravitational wave event increases our detection confidence. So having multiple detectors registering this event is really, really important and crucial for us. And in particular, it gives us improved sky localization if we have detectors that are distributed around the globe. And this is quite important when you want to do electromagnetic follow-up or neutrino follow-up. And you would like to know which instrument is best to query in order to look at that patch of the sky. It can also help us measure the polarization content of gravitational waves better. And of course, if you have multiple detectors across the globe, not just 1 or 2, chances are you'll always have 2, or you will have a higher chance of having 2 operating at the same time and have an increased duty cycle. So reducing the risk of losing an exciting gravitational wave event. The detections I'll be talking about today, at the moment, they will all have come from the combined network of LIGO and Virgo. So I'll not be talking about any geodata, and also not about CAGRA data. So where do we stand at this moment in time? The Advanced Detector Network came online in 2015, towards the end of 2015 in September, and underwent its first observing run, which lasted until the end of January 2016. As you can see in blue here, the only operating detectors were the 2 LIGO detectors in the United States for that observing run, and we had a double coincident time, so Hanford and Livingston operating in coincidence of about 49 days. There was quite a long commissioning break afterwards, with various upgrades to the detectors to increase the sensitivity and hence our reach for gravitational wave events. And that started back up at the end of 2016 and ran until the end of August 2017, with a double coincidence time, so between Hanford and Livingston, of about 118 days. And at the end, you can see here, the Virgo detector in Italy joined this effort and came online for a period in August, contributing to a triple coincident time of 15 days in total. And that was very exciting because a lot of exciting observations were made during that period. Then you can see detectors were off for quite a long time. There was quite a significant commissioning break with significant upgrades to the detectors, in particular the implementation of frequency-dependent squeezing, which significantly improved the detector sensitivity. And it came back online in April 2019 for the third observing run. And the third observing run had a small break of a month between its two halves. And so we split this into O3B and O3A. We accumulated a triple coincidence time in the first 6 months of about 81 days and a triple coincidence time of 75 days for the second half, which was cut short by the COVID pandemic. Here you can see one of the metrics to measure how the significance, how the detector sensitivity improved during these upgrades. The measure that is shown here is what is called the binary neutron star range. As a function of time, the binary neutron star range tells you how far the detectors can see a binary neutron star collision at a signal to noise ratio of 8. And we can see here from O1 to O2, and then the two halves of O3 here. And you can see that the improvements have been quite dramatic. With the end of O2 here, we had a sensitivity of about 100 megaparsecs in the range for LIGO Livingston, and this went up significantly to 140 megaparsecs in the third observing run. And you can see also good improvements for all the other detectors. In particular, I should note Virgo here, which came online at the end of O2 with about 30 megaparsecs reach, and then had significant improvements up to 60 parsecs, so doubling the range towards the end of O3. Now, having a wider reach, of course, allows us to observe many, many more interesting events in the universe at a certain SNR. Since I'm talking to particle physicists, I thought it might be useful to give you a brief overview in a very, very basic schematic of how the pipeline works, so to say. So we have some gravitational wave event taking place in the universe, hopefully numerous detectors operating at the same time and registering a candidate event through an online analysis. So the data are being analyzed in real time. And this is really important because low latency does actually really matter for electromagnetic or neutrino counterparts that you might be searching for. So there is the aim of having a very, very low latency analysis to communicate with external partners, and Elena is going to talk to you much more about that in the next talk. There's also, of course, data quality continuously going on in the online process, but then also after essentially a run or a chunk of a run has already been conducted and data is looked over again to understand the behavior of the detector, improve the calibration of the data, etc., etc. And if there's an interesting event, of course, more detailed analyses are conducted in order to validate the astrophysical origin of that event. When all of this is done, we also perform afterwards, when we have completed a certain amount of observing time, to perform offline gravitational wave searches. So here we make use of a better understanding of the detector and the cleaner set of data. And once this is done, we also perform, of course, detailed Bayesian inference in order to determine the properties of the sources that have created these gravitational waves. And once you have all of that, you can do the exciting science, which I put here 4 main pillars, I would say, where we have, of course, the astrophysics, but you might also be interested in testing general relativity. These collisions give us, an opportunity to look into a regime in the deep in the gravitational potential that we can't probe with solar system probes, for example. We can also contribute to cosmology understanding, which is particularly interesting now that the Hubble tension is essentially at 5 sigma. And of course, fundamental physics, here to highlight in particular, of course, our understanding of the equation of state of neutron stars. How do we identify events? So I guess similar to what happens in colliders, there's a lot of information coming in. So how do we identify events and keep interesting ones? Well, when we search the data, there's essentially 2 algorithms that are being used. There's either a modeled search where we have theoretical knowledge, which is possible, for example, when we specifically look for binary neutron stars or black hole binary collisions, which is a matched filter search. So here we just take these theoretical templates as predicted by general relativity, we call them waveforms, and we compare them against the data. So you can do that very, very quickly and in a complicated as complicated as you would like to do. Or if you don't want to rely on this, just looking for signals that you essentially know what the shape of the waveform should look like, you can also do a coherent excess power analysis where you look at excess power statistics correlated between different detectors. So once you have your trigger list, you probably don't want to keep everything, so you want to assess the significance. And there are essentially two ways of looking at this that people have used in the community or are using in the community. So one is the false alarm rate, which does just tell us how often do we expect a noise event to produce an event with the same ranking statistic as an actual astrophysical event. And that's the basic quantity that is often produced by the searchers directly. Now, the alternative to that is the astrophysical probability, because now that we actually have observed these events, we also have some understanding about the astrophysical merger rates of black holes and neutron stars. And so we can take this into account and then compare how the foreground and the background ranking statistics distributions do compare if you take into account that you expect that many black holes mergers to happen or that many binary neutron star mergers to happen. So both of these are used, and I should warn you, people make different cuts on these, and that of course will impact how your trigger list that you analyze or your event list looks like. Now, with the choices made by the LVK, and we are not the only people analyzing gravitational wave data, data is public, so other people have looked at this too, and they may choose different boundaries. But here for the LVK events, we are now at a total of 90 confident gravitational wave detections that pass our various cuts that have been chosen, not always consistently, to be perfectly honest with you. And you can see here the noise increase, which is of course strongly correlated with the dramatic improvement of the detector sensitivity after the second observing run. And we're now standing at a total of 90 gravitational wave detections, and all of these are consistent with the gravitational waves from compact binary mergers. Now, compact binary mergers, when I say that, I refer to either black holes or neutron stars or mixed binary consisting of a black hole and neutron star. And here we're talking really in the range of stellar masses. So a few times the mass of the sun to maybe a few hundred times the mass of the sun. More massive objects would give us gravitational waves that are too low in frequency to be detectable by ground-based detectors. Now, these events that we're observing, they are kind of towards the end of the binary lifetime. And that means that the gravitational wave signal looks like a characteristic chirp signal, as we call it. So the gravitational wave frequency, as the signal sweeps through the detector band, changes over time, which you kind of see in the sketch here. Gravitational waves are being emitted, so the orbit shrinks by conservation of energy and momentum. And you can see that consequently, the frequency of the waves goes up until the two objects merge, they collide, they merge. And if you have two black holes initially, then GR tells you that the object that comes out at the end is also meant to be a Kerr black hole, and that's something we can test with gravitational wave observations. Now, when we want to, now of course we want to know, is it actually a black hole or neutron star that's producing this? So again, we use these waveform models that I mentioned before to extract the source information. In the context of black holes, that's masses and spins. And if we also have neutron stars, then we can also obtain information about the tidal properties of these stars. And having done that, here you can see the stellar graveyard of the LIGO Virgo Cagra black holes in blue here. And what you should take away from this plot, they're very numerous, obviously, but they also span a very, very wide mass range. And in particular, they span a mass range with probing masses that are significantly higher, in particular, to the ones we already inferred from electromagnetic observations in stellar binaries. So where you have a stellar component and postulated a black hole, and you can infer the mass indirectly, for example, through accretion processes. What we also see is we have masses of black holes that are also quite small, so they're reaching into what was previously thought to be potentially an observational mass gap, so black holes less than 5 solar masses. And we have also observed neutron stars and some objects where it's not entirely clear, at least not from the gravitational wave signal alone, whether they are neutron stars or black holes. So 90 is too many to talk about, so I've picked a few personal favorites to tell you about some exciting things that we have observed in that vast sea of black holes that we are observing. First of all, GW 190412, which came quite early in the third observing round, and this was the first clear detection of a binary black hole signal that had an unequal mass ratio. So up to this point, all the observations were consistent with equal mass black holes. But here was the first clear signature. You can see here the mass ratio distribution, and here the chirp signal as it sweeps through the band. That was clearly something that needed a much larger mass ratio, much smaller mass ratio, depending on your definition, than equal mass. And this is quite interesting because you ask questions, where do these black holes form? What are the progenitor stars? In what sorts of environments can they form? So knowing about the masses and knowing that there exist quite asymmetric binaries as well is very, very exciting for the astro community. Not much later, we had GW 190521, which at this point was the most massive binary black hole detected at this moment in time, having 85 and about 66 solar masses. So really, really heavy black holes. And in particular, the remnant was found to have about 142 solar masses. Now, this is very, very exciting because in particular, the remnant mass is what is called an intermediate mass black hole. And intermediate mass black holes have been postulated for a long time. There were some electromagnetic candidates, but there was no really convincing confirmation. And many of these claims went away over time. But this one looks very, very consistent. People with independent analyses and under very different assumptions have come to similar conclusion, not the exact same numbers, but all of them lying in the intermediate mass black hole range. What's also interesting is actually the masses of the progenitor black holes, which are larger than what is predicted to be able to form from a standard stellar collapse. There's something called a pulsational pair instability, and that produces a mass gap. And we did not expect black holes to form in there. So it's, again, from the origin of these, interesting to ask, could they potentially have formed from multiple mergers, and so on and so forth. So again, something really exciting for the astro community. And then it was in August, GW 190814, which was also very exciting, as it was highly asymmetric at a mass ratio of around 10. But in particular, the component masses of the secondary were rather puzzling because the secondary object is heavier than the heaviest known neutron star, but lighter than the lightest known black hole. So it sits in this awkward place in mass space where, both are potentially possible depending on the assumptions of the equation of state of the neutron star and the spin of the neutron star. But it's also, an interesting question to ask you, how could such a small black hole form if it were a black hole? It's difficult to reconcile with the maximum neutron stars, as I just hinted. So could we look for a tidal signature? Yes, we can, but unfortunately, because of the high mass ratio, tidal signatures in the gravitational wave signal are suppressed, and essentially our analysis just returns the prior. So no additional information on the tides. And then you can say, oh, could there potentially be an electromagnetic signal? And could our partners point a telescope and give us a hint that there was indeed some baryonic matter in the process? And the answer is, unfortunately, we find the black hole spin to be very, very low. And that makes, in combination with this very asymmetric mass ratio, disruption events even more unlikely. So it remains a mystery and has been subject to a lot of papers and speculation, I would say. And then very, very excitingly, up to this point, everything was either binary neutron stars or binary black holes. And then in January 2020, the first neutron star black hole binaries were identified from the gravitational wave signal. This is a statement, again, purely based on masses here. And you can see the confident detections here in colors, including also one that was made at the end of 2019. And there are also two other candidates who are marginally consistent, but in tension, depending on the uncertainty of the maximum mass of the neutron star and the consistency with that. What about the spins of black holes? So most black holes that we find in the binaries are consistent with having small spins and spins that are somewhat positively aligned with the orbital angular momentum. But there are some tantalizing exceptions in the data set. In particular, this GW 190521, so this intermediate mass black hole I talked about before, shows spins that have a concentrated probability distribution towards an inclination. And if you have spins that are misaligned with the orbital angular momentum, which is shown here in the spin disks for the primary spin and the secondary spin, then you induce something called general relativistic spin orbit precession, or Lense-Thirring precession, depending on what you prefer. And that induces a very characteristic modulation in the gravitational wave signal that's kind of illustrated at the bottom here, where you can see a waveform that is no longer just a chirp, but it has very, very clear modulations. And these depend really on the orientation of the binary and how much processing spins or how much in-plane spin component you have in your binary. There's also one later on the 29th of January 2020, which has a very strong concentration of the primary black hole spin towards really the 90°, so the in plane, the instantaneous orbital plane of the binary. And for 191109, here we can see something that is maybe not so strongly processing, but definitely has a probability distribution more pointing towards a misaligned, so more a retrograde orbit in the binary system. So that is very interesting on an individual basis. But we can also, of course, look with all these observations at population-based statements. So now we have a reasonable statistic, so we can look at the underlying astrophysical distributions that would give us these observations. So in particular, if we look at the mass spectrum of black holes, we find that the primary mass distribution, which is shown here, is consistent with a power law distribution that has a Gaussian feature at around 34 solar masses here. This is a very simple model here, and it shows you how it changed with the observations we had in GWTC2 to the observations in GWTC3, where we increase, obviously, the number of black holes. Features we do see that seem to be reasonably robust between these two analyses is that the spectrum turns over quite sharply at about 7.8 solar masses, and the minimum mass of the black hole is about 2.5 that we found. Now, if you allow for more complicated models, in particular non-parametric models with some mixtures in them, which is shown at the bottom here, in addition to these kind of global features, we also find a little bit of substructure, so additional peaks that are popping up as we allow for less constraining and more flexible models to fit the underlying population of the black hole masses. So, of course, we'll see what the future holds when we'll observe more and, maybe also more black holes at the higher mass spectrum here. For the spins, the story is also quite interesting. Again, this is here the black hole spins. When we look at the spin parameters here compressed into two parameters, chi effective, which tells us about the aligned spin components, so the components parallel to the orbital angular momentum, and chi p, the ones orthogonal to the orbital angular momentum. So these are the ones that would give us some indication of precession here. And we see in the underlying population that our observations are consistent with an astrophysical distribution that is slightly shifted towards a positive chi-effective, which is kind of consistent, as I said, as what we've seen before. Most of the spins are small and positively aligned, but there is a tail to negative ones. And also there is a weak evidence or weak hint that the population, the underlying population, actually requires precession. Looking at all these black hole mergers, of course, they don't happen just at one moment in time, but they're distributed in time or in redshift. And so by looking at our data, we can reconstruct the merger rate as a function of redshift. And we do find with the current observations that the binary black hole merger rate tracks the local star formation rate. Now, at some point, we expect this to turn over, but that requires us to observe black hole binaries to further distance. And here you can see them having observed all three types of compact binaries, what the current inferred merger rates of these are. So for the last 3 minutes, let me say a little bit about fundamental physics that we can do with the gravitational wave observations. I think particularly interesting for this audience is what we can say about the equation of state of neutron stars. So binary neutron star gravitational wave signals have a characteristic imprint of the tidal interactions that's very different to black holes, which do not have this particular tidal interaction. And this changes the phasing of the gravitational wave signal, which we are very susceptible to. And we can reconstruct, so this phasing, this dephasing parameter relative to the point particle depends on a macroscopic parameter, lambda tilde, which is the binary tidal deformability, which is directly related to the equation of state. And in the first observation of GW170817, we were able to, for the first time, constrain this parameter, and we find it to be consistent with soft equations of state on the spectrum. So here, equations of state that give you small neutron stars, about 11 kilometers in radius, and have very little tidal effects. Now, rather than just using these macroscopic parameters, I think folks in the nuclear community are, of course, more interested in looking at the pressure as a function of the central density. And we can do that by reanalyzing the data with a parameterized equation of state, which is continuously connected at various points as you go deeper and deeper into the star. And you can see this in the curve here, the inference for GW170817 of the distribution of the pressure as a function of nuclear density. The other side, on the fundamental physics side, is of course the question whether GR is still the correct theory at that energy scales. And why do I say at that energy scales? Because black holes, actually, these collisions that we're observing here, they sit in a very nice place in the curvature potential plane, as shown here in this plot by Nico Yunus. And that's something we can't probe with any other experiments that we have made to date or measurements in our solar system. And so we can test whether in this regime GR is still the correct theory, or whether that's already an energy scale where we need to consider modifications to general relativity. And there's a whole, a vast sea of tests you can perform. One of them that's quite interesting is the residual power. So here, if you remove your best fitting GR signal, is the residual consistent with Gaussian noise, or do you have something unexplained that's left in the data? And we find after GWTC3, so the third observing run, that everything is still consistent with GR. By looking at the dispersion relation for gravitational waves, we can also constrain the mass of the graviton, which is now constrained to being less than 1.27 times 10 to the minus 23 EV per c squared. And there are many, many other tests you can perform, but the upshot is that to date, we have found no conclusive evidence for new physics beyond GR. So to summarize, I think it's been exciting, not even 7 years of gravitational wave astronomy, where we have now found a total of 90 confident gravitational wave detections, with 35 having been added in the last 6 months of the second observing run. The majority of these events are binary black holes with a very diverse range of masses and spins, both in the upper and the lower mass gap, which is quite interesting. We have seen the first confident neutron star black hole detections, and also the first intermediate mass black holes. And we now have actually 2 confident binary neutron star observations. There's obviously lots more to say about the astrophysics and so on and so forth, and it won't stop here. So this is just the beginning, I like to say. We are scheduled to restart operations at the end of December, at the end of this year in December 2020, and then we'll have operating a full detector network with Kagra now joining the full observational effort. So with this, I'm going to stop here. Thank you very much.
Okay, thank you very much, Patricia. Amazing to hear about all the results from this. So questions, please. Yes, Chris.
Many thanks indeed. Very interesting presentation. If you go back to, I think it was about slide 8 or so, you were talking about the fact that there might be some, a bit later than that, sorry, it's 18, I don't write the number down well, where you have precisely this one, where you have the populations. So what is your thoughts about this structure that you're seeing here and what we can potentially learn for this? Could you say a bit more about that?
Yeah, so I'm not a populations person, to be perfectly honest, but my understanding is, there could be subpopulations, that there are particular subpopulations that prefer different formation channels, that prefer the, the creation of black holes in these particular mass ranges that could come from, that's up to debate for the people who do the stellar synthesis, to see if they see certain distributions that peak at certain mass intervals, for example. That could also, of course, be, obviously, since these models try to find the underlying astrophysical distribution from our data that we fit in, right? That could also, of course, be maybe an observational bias here. It doesn't look like that at the moment, right? Because we actually have quite a broad range. Could also just be, of course, that, certain types of black holes with certain masses, they form maybe more often and also merge more often if they happen to be in particular environments where they are being formed, right? So that could also be the case. So that's at least my understanding.
Okay, many thanks.
That answers it.
Thanks again for the great talk.
Good. Let's move on to John.
Could you show us the spin plots with the 2 semicircles and give us a brief primer on how to read these? They weren't immediately clear.
Oh, I'm sorry about that. So if you read the x-axis, you can see the magnitude from 0 to 1, where 1 is the Kerr limit. So beyond that, you wouldn't have a horizon, but you get a naked singularity according to GR. And if you look at the axis, so the tilt here, that is the inclination between the spin and the orbital angular momentum. So that's the quantity that drives precession. So if you're perfectly aligned or anti-aligned, you don't have any precession. And if you start to incline your spin relative to your orbital angular momentum, either for the primary or the secondary, you'll start to see spin precession effects. They become stronger as you go really into the orbital plane, the instantaneous plane, so you maximize that effect, and they go to 0 as you go to perfectly aligned or anti-aligned, so if you're 180 or 0 degrees.
Thank you very much.
Okay, and I see we have a question from Marco as well.
Yeah, thanks for the great talk. My question was about the international coordination between the different observatories. So you said you're starting in December. So are future runs completely agreed between all the different sites in order to maximize the full coverage?
Yeah, so the runs are fully coordinated. I mean, if we talk beyond, 04, we'll have to see what the status is. So, for example, like India may be already ready for 05, so they're observing one after that, which would be great. So we have a joint operations committee that takes care of that, makes sure that it's understood, what the progress is and at what point they can join the run. On the data analysis side, which is what I'm working on, we're always working as soon as we know that there is a possibility of these effective networks to join, to make sure that the pipelines are updated to handle the data streams and make sure that the analysis uses fully coherent analysis between the end detectors that are operating. So CAGRA, for example, it will be fully integrated in all the analysis, at least on the compact binary side, parameter estimation, for example, from 04 onwards.
All right, thanks very much.
Okay, thanks a lot, Patricia. I think we have to move on. Lots of great questions here. If there are more questions, then I hope, Patricia, that you will be able to look in Mattermost as well, if there's some questions coming there. I know I have one myself, so expect one at least. We should move on to Elena Cuoco, that will talk about multi-messenger detection. I'm not good at that. And we've, of course, already heard a little bit about that. So it'd be great to hear on the next part of that in much more detail. So Elena, please go ahead whenever you're ready.
Thank you. Thank you very much. Can you see my screen?
Yes, we see and hear you well.
Perfect. So thank you again for the invitation for this talk. So now I'm going to talk a bit about the multi-messenger astrophysics, but mostly linked to the activity on machine learning and the perspective of the kind of analysis that we can do with the multi-messenger information. In particular, if I have time, I wanted to talk about two projects we are working on in the two European projects, ESCAPE and EOS Future. One is linked to the multimodal machine learning application to astrophysics, and the other to a real-time analysis for gravitational waves based on the European Open Science Cloud system. So why we give so many importance to multi-messenger astronomy? Because there are information that we cannot have using only gravitational wave signal that give us a lot of information, but not enough to fully characterize the events that produce these gravitational waves. So we can use this complementary information to have a precise picture of what is happening in this kind of events. So we could have more precise sky localization as it happened. We can identify the host galaxy, so we can have also a better estimation of the distance and of the redshift of what is happening with the local environment that produce this multi-messenger information. So as you already heard from Patricia, the first event that has this characteristics was the GW170817. This is our first multi-messenger events. It was produced by two neutron stars with a huge signal to noise ratio that let us see the event in its completeness, and it lasts for more than 100 seconds with this 32 signal to noise ratio. What we expect from this kind of events is that they could have the electromagnetic counterpart, because the presence of the neutron stars or of massive neutron stars can produce different emission in the multi-messenger wavelength. In particular, we expected to have a short gamma ray burst linked to this kind of events, and the kilonova, the emission in radio, and and in infrared emission and so on. This is what we expected, and this is what we we found out with this event, because after 1 second and 7 second, we identify together with the gravitational wave emission also a gamma ray burst. In a few hours, we see the events also in optical counterpart that let us also identify very well the galaxy where the event happened. Then after some days, we see the emission in X-rays and in radio afterglow. This made us to have a full picture of what is going on, and a lot of physics also linked to this kind of event. The gravitational waves and the multi-messenger are not only linked to the binary neutron star collections, but we expect also to see this kind of emission also with other astrophysical events, such as the core collapse supernova. So we expect to have, for these two events, emission in gamma ray bursts, short or long gamma ray bursts, but also neutrino emission, especially for core collapse supernova, and all the other electromagnetic emission. So it is important that we start thinking what we can do with this kind of information. I want to talk now just briefly about machine learning application that we already started in LIGO Virgo collaboration, and why it is important then linked to the multi-messenger analysis. So as Patricia said, we have two kinds of search that we usually perform. The one that is linked to the modeled search, because we know very well how to model the binary collection events, at least numerically or analytically, while it is not so easy for core collapse supernova, where we don't have a clear theoretical model of what is happening, so we have to rely on numerical simulation. So we have these two kinds of different search. And for each of them, we are developing also alternative algorithm to detect, to identify the events. For example, for the core collapse supernova, we started some machine learning based approach where we simulated different waveform signal with a different model, and try to see if with the machine learning we are able to identify correctly the different waveforms. So the idea is that once we are able to detect one of these events, we could understand better which is the event that which is the physical mechanism that produce this kind of emission. So what we did is to simulate, to use this numerical simulation injected in Virgo, LIGO noise and Hassnae telescope noise, and try to apply this machine learning pipeline to classify the event. And the typical waveforms in this kind of pipelines is this one depicted here. So we have the noise that could be different from the detector that we are dealing with, the waveforms. We add this signal, we identify the triggers, and then we start this different classification. And this is important even because very often in our data there is the presence of signals, noise signal that can mimic the gravitational wave present. So it is important that we are able, even for the low latency system, to be as fast as possible to identify and disentangle signal versus the noise. And this is just an example of application to core collapse supernova, where we use 3 different detectors on real data, where we injected this signal. And you can see that in this confusion matrix, where you see see how good you are in predicting the right event, there is a good accuracy for most of these waveform, not all of them, because some of them are very low signal to noise ratio events. Then another example that I want to show is on the CBC signal, because we can use, as we are always using the mutual filtering pipeline. So we know the waveform, and we try to look for similar waveform with the different parameters in our search. But we wanted to move also to something that is agnostic with respect to the waveform modeling. And this is an example of application that use autoencoders. So the idea here is that we inject this kind of signal, CBC signal, we have a background noise, and we try to reconstruct in some way the background noise and identify as anomaly the signal. And this was an example of application. So we have, as usual, these two kind of inputs, so noise and waveform. And with this autoencoder deep learning network, we try to identify the anomaly versus the noises. And as a byproduct, we can even reconstruct the anomaly itself, so our waveform. And this is an example of what we realized. We identified the three different detectors with the O2 data, the excess of a signal with respect to the standard noise that for us are the anomaly. And we try to reconstruct some of the signal using the information of the autoencoder. And these are examples of real data, of real signal that were in our data. And you can see that the reconstruction are not so bad. So in principle, this could be one of the fast pipeline that we can use to detect this kind of signal. These are other examples with the low signal to noise ratio. Machine learning is not only applied for the classification. In LIGO-Virgo collaboration, and we are using machine learning, and we start using in many other fields. One important field that I wanted to underline is the parameter estimation, because as as Patricia said, one important step in our data analysis is to be fast as much as possible in giving outside the alerts. So the first parameter estimation part should be fast in order that we can send to the external colleagues the parameter of our events. And this, for example, the sky localization is fundamental for the telescope that have to point in this sky localization. So there are a long of activity in this direction. This is just an introduction on the kind of new alternative data analysis method that we are working on. Now I want to move forward to the multimodal machine learning. So what is multimodal machine learning? We know that in the world communicated with us with different modalities. So we are our brain is used to interpret the information that we receive. So that are visual, text, speech, any kind of information that we receive from an event can let us to understand better what is happening. And this is usually used in other kind of analysis. We can better use the information, performing dedicated pipeline to the different nature of the input. So if we have image, we can use a dedicated pipeline. If we have text, we can use a different one. If we have a speech or signal, we can use a dedicated one. But at the end, we can merge the information that we are able to extract from this different input. And this is a typical multimodal machine learning pipeline. We encode in the right way the future that we can extract from these different modalities, concatenate, and we can perform our classifier regression task to have better results on the prediction. So we start, sorry, this is just an example, a list of place where this is usually used. So multimodal machine learning is used in many other fields, let's say medical applications, picture recognition, robotics. So each kind of situation in which you can learn more by analyzing all this information together. So our idea was to apply this multimodal machine learning to astrophysics. Why? Because as I said at the beginning, our events can send messenger in different modalities. So we can receive the gravitational waves, the electromagnetic counterpart, the neutrino information from the same events. So when you have a binary neutron star or core collapse supernova that is exploding, you can receive all this information that could be used to better reconstruct the physics of the event. So this was our idea. Let's start from a multi-messenger events, see which are the different modalities in which it happens, find the right representation of the information, because usually in gravitational wave analysis we can use we are used to work with the time series, but very often we prefer to move to image, so time frequency representation, for example. Then we build a dedicated model for each of these events and merge and concatenate the information to do the right prediction. So this was the general idea. We decided to make some test, some proof of concept of this idea, just using two modalities, so the gravitational wave and then GRB signal. What we did, the idea is that we can use this information to predict the redshift. So we know that for some GRB events, you don't have all the complete information to the redshift in which they happen. So we see if adding also the information from gravitational waves, we can have a better prediction. So we prepared a data set in which we have a bunch of binary neutron star and associated GRB events. And for some of them, we know the redshift, and we want to predict the redshift for the others. So this is also a typical way in which machine learning pipeline works. We train on what we know, and we try to predict the unknown. The idea that we developed started with this generation of a population of binary neutron star. For each of these, we associated a GRB as observed by Fermi-like detector. These are the typical distribution of the neutron star population. So we go until 500 megaparsec with only mass in the binary neutron star range. We used the Einstein telescope noise, so we because for this kind of events, better sensitivity, better it is. So we move to the future with the Einstein telescope. And we simulated the GRB using the Patricia et al. Model for the afterglow that are similar to a GRB that is used as a prototype. So each of these binary neutron star has this associated gamma ray burst emission. Then we move to the representation. As I said, we can use different representation. So typically for the GW events, we use the time series. We decided to model, to transform this time series in a wavelet map using this representation. And instead we decided to use the light curve, so 1D representation for the GRB. So we used the 70% of our data set to train the pipeline and the rest to validate and test the results. We build this network, so dedicated to the different representation. So for the 2D gravitational waves, we use a convolutional neural network. For 1D GRB light, we use a convolutional neural network in one dimension. At the end, we concatenate the results of the two networks to do the prediction of the redshift. And this is the results. So the results are not so bad. So we are, especially for a low redshift, the prediction are good. Not so bad, not so good for the high redshift, but this is what we expect because these are essentially linked to the signal to noise ratio. So this is encouraging for the kind of activity that we want to do. So we want to start using different information. So same event, different nature information to have a better estimation of some of the parameters. Since I have still time, I wanted to also introduce why we are working on this idea and what is behind what we want to do more. So low latency pipeline is fundamental, because we have to send alert as soon as possible. So there are a lot of activity that we have to do before sending alert. So we, as Patricia showed, I have this online pipeline that running the detection of the event and the first parameter estimation. But we have to deal also with the noise. So there are the data quality check that we have to do before sending alerts around. So typically we can send the good information within 1 hour. And then we start to refine the parameter estimation with offline analysis to better identify the event. So it is important we be fast, and we try to optimize this part. So there is work done, as I said, in machine learning to boost this part. So at least for the data quality, where we can easily identify noise versus signal, it is important if we can apply some of this pipeline there, but also for the parameter estimation. The idea behind this project is, are we able to set up a real-time alert for gravitational waves based on the new idea of the way which we have to do the analysis in the European framework, so the so-called European Open Science Cloud. So the idea is that we can build some infrastructure in which we receive data, analyze them, and publish it as soon as we have the results. So we set up this idea with this Wayfire. So the idea is that we use the new technologies as Kafka cluster to receive as a Kafka system to receive the information, to analyze the data using machine learning and dedicated GPU, to put the results in a database, and to show the results with the classification. This was the starting idea, with having in mind the fact that we wanted to show in real time the signal, the trigger, and the classification. So we started working in this direction, and this is one of the projects we are developing in this EOSC future framework. We want to move forward. So the idea is that why don't we try to set up this kind of machinery also for multi-messenger events? So adding also the information of gravitational wave short GRB events for the binary neutron star, or in case of a core collapse supernova with the long GRB. So we are working in this direction. And the vision is that we can do this even with the neutrino data. At least the quasi-simultaneous events information can be analyzing in the future in a real-time way. Then for sure this analysis can also be used for offline, when you can integrate also the optical data. And in this way, you can maybe have a better sky localization information, parameter estimation, using all this input data. So I'm going to the end, so I also be faster. So what's next? This is what we are working now on this, and we hope to start integrating the information from these 3 different messenger. In particular, we are trying to set up a memorandum of understanding with CTI and KMM3net to start having at least simulated data, to go on with the idea of this multi-messenger alert system, where at some point in the future we can integrate a gravitational wave, GRB, and neutrino information for sending out alert to the other telescope. And thank you for your attention.
Thank you very much, Elena. Great to hear this here. So open for questions. Nobody else is jumping for you, Chris, so you'll be first again.
Good, many thanks, Ulrich. Thanks very much, Elena, very interesting. I was interested to hear about your alert system, and you have a human vetting stage, as you said, in this. Yeah. is the human vetting stage going to be there in the long term? Is it something where you could imagine that you can really automate out?
No.
At the moment, what kind of rate of human vetting of signals? What kind of rejection rate do you actually have for the human rejection?
So I wrote human vetting, but I have to confess that now most of the things are automatized. So the data quality, we have a veto system that is in some way automatized a lot, not still based on machine learning pipeline, but on other kind of pipelines in which you analyze coincident signal with other environmental sensor and so on to check if there is something. I have to say that when you are talking about 3 coincident detector, there are few events that you have to check really in using human vetting. So the point is that on the single detector, this is important because when you have to say okay, they go, the single detector has to say that the data are good. So there is the human vetting. So the people that are in control room do a first check on the data quality. So check different channel and say, yes, so we have green light or not. So this could take time. So the idea is that we try to automatize as much as possible on this part.
Okay, many thanks.
Okay, we have time for other questions. So please put up your hand or just speak up.
Right, maybe I could go work if that's okay.
Yes, go ahead, Graham.
Yeah, thanks. Elena, thanks a lot for that very interesting talk. I was wondering, so specifically about the machine learning training that you need to do. You're incorporating data from many different sources and data that means different things. And how difficult is it to pre-process the data so that you can make sure that the network can learn the relevant features from each of the very different data sets that you have? And I was wondering if you'd learned anything about different types of architectures that sort of incorporate and filter and process the data in the most scientifically meaningful way, let's put it that way.
Okay, there are, thank you for the question, because there are 2 different ways of approaching to this kind of analysis. So there are people that think that to simply use a deep network, you can learn whatever you want. In practice, what we prefer to do, that most of us doing this kind of analysis do as a first step is the whitening procedure. So we try to remove from our data at least what we know. So the stationary noise is the first part that is removed, because we don't want that machine learning pipeline spend time to try to learn something that we are able to learn with the standard algorithm. So usually the first step is the pre-processing. And this is done as a standard signal processing. So some of us also can use filtering the low frequency, because we know that there the noise is too high to learn something. But once you do this minimal pre-processing part that is standard, we let the network learn the things.
Okay, thanks a lot. That's very interesting.
Okay, let me ask a question as well, Elena. In particle physics, we're very used to training neural networks in many different ways in simulations, which I think you're relying on a lot here. But then we very often use control channels as a way of validating how it performs on data from our detectors. Can you do something similar, given that the number of gravitational wave signals you actually have is pretty low? So how can you validate that your simulations you train on are actually of high enough quality?
But, usually we start with the simulation. So this is the standard procedure also for us, where we simulated the signal. So we can inject as much as signal as we want in our data. Sure. And then this is was what we did also for the core collapse supernova, especially in this work that we did. We don't use some particular waveform. not even in the training, because we wanted to see that if you train on a kind of a data set, if you are able to identify also what the network was not used to see in the training data set. So this is something that we do as well, so as a standard way to check. And then we always start with the simulation, but we move forward with on the real data. So we have real data where we can inject our signal, so our waveforms, and we can predict the same in a difficult environment, because as I said, there are noise and the other. So it usually works well. I have to say that obviously this is linked to the signal to noise ratio. So if you go to low signal to noise ratio, this is difficult.
Okay, I see. Thanks a lot. Marco, we've just got time for a question from you as well.
Yeah, just a quick one. I was wondering, do you use any specific hardware for the machine learning, or is it all on standard CPU hardware? Do you make use of accelerators in any way?
No, we use GPU. So this is run on Tesla GPU, not on still on cluster of GPU, because we don't have, at least in Virgo, we don't have. We have to use the LIGO one, but it is not on specific hardware. So never tried the TPU, things like this, but we work on GPU.
Okay, thanks.
Okay, thank you very much again, Elena. So more questions again, please move them to various chat channels. If you have them, we should move on. So, so next on the agenda will be 3 short presentations from the poster prize winners, and Martha Hilton, that's been involved in organizing that, will introduce each of the 3 in turn. To the speakers, when you speak, it's very short presentations, so I will only give you a 1-minute warning, so please try to stay on time. So over to you, Martha.
Hi, good morning. Thank you, Ulrich. So it's my pleasure to introduce the winners of the poster session. I was co-organizing and judging the poster session with Marco and Nicola McConkie from Manchester. And thank you to all of the participants in the poster session, both those who presented and those who attended and provided some very interesting discussions. So we decided the winner based on both judging and also the people's choice, so from all your votes. So thank you to those who voted. In first place, we have a very nicely presented poster with a very clear 5-minute video, which I enjoyed, as I'm not an expert on this subject, and she really explained some simple concepts very well. So it's my pleasure to introduce the winner of the LeptonPhoton poster prize. That's Hassnae Jarrari, with a high granularity timing detector for the Atlas Phase 2 upgrade.
Thank you very much.
Hi, Hassnae, thank you.
Me and you can see me.
Yes, all good.
Perfect. Then I can go ahead with the presentation, maybe.
Yes, please do.
Okay, so first of all, I'd like to thank very much all the conference organizers. I'm sharing my slides. It was really a pleasure to join these rich and diverse lectures this week, and of course, I'm extremely delighted and honored to be awarded the first prize of this Lepton Photon conference. My name is Hassnae Jarrari. Thank you for the introduction. And I'm a PhD student at Mohammed V University in Rabat, in Morocco, in collaboration with the Academia Sinica in Taiwan. And I'm working on the Atlas experiment. So let me now explain very briefly my poster. I think you can already see my slides.
Yes, all good.
Perfect. Okay, so my poster was about the high granularity timing detector for the Atlas Phase 2 upgrade. As you know, in the high luminosity LHC, we will have, which is foreseen to start in 2028, we will have 10 times more luminosity, and hence we will have very high pileup of 200 proton-proton collisions, as you can see here. That means that we will have almost 1.8 vertices per millimeter square, per millimeter. Sorry, And you can see also the 200 proton-proton collisions here in this event display. And that means that we will have difficulties in well separating the pileup jets from the hard scattered jets. For this purpose, the Atlas detector will be upgraded, and we will replace the current inner detector by the inner tracker that will cover an extended pseudo rapidity, and will provide a better resolution on tracks, position resolution. This will help a lot in the central region, while in the forward region, we will have the EGTD, which is the high granularity timing detector that is a two instrumented double-sided layer. As you can see it here, it's built in this 3-ring layout because we have different amount of irradiation along the rings in such a way that we will have to replace the inner ring after 1000 inverse femtobarn, and we will have to replace the second ring after every 2000 inverse femtobarn, and then the outer ring here in purple will never be replaced. So it will be installed here in this gap region, this very little gap region between the barrel and the end cap calorimeters. And for this tiny place that we have, we chose to use the LGAT technology, which will allow us to have this detector in 75 millimeter thick. And the high precision timing measurements of this detector between 30 to 50 picosecond will allow us to assign time to each track in the forward region, as well as improve the pileup rejection and correct track to vertex association. So we can see here the models of these detectors. They are built of the 2 LGAT sensors bounded to 2 ASICs. And then, yeah, so here I explained what are LGATs, the low gain avalanche detectors, which are basically neutron, proton, silicon detectors, as you can see here, with additional, and you can see it here in this blue gap region, additional and very thin and highly doped p-type multiplication layer with high electric field. And we have the prototypes that are produced for the EGTD are from different manufacturers, like mainly CNM, HPK, and FBK, and NDL. So the size, you can see it here, is 1.3 times 1.3 millimeter. And to read out this signal from these LGATs, we use the Atlas LGAT timer readout chip. It's called Altiroc, which is made of 2 parts, the analog part, like preamplifiers, time of arrival, time of threshold, over threshold, and then we have the digital part for data buffer and transmission. And of course, we have tighter requirements for these readout chips. In terms, for instance, for the time resolution is less than 25 picosecond. So also for the radiation hardness, we have made many studies about this. And the radiation tolerance for both the LGATs and the readout, the Altirocs, is 2 mega gray. And you can see here the different, the improvements of the time resolution after the replacement of each ring, the 3 rings. And finally, of course, we are working on different studies for the performance measurement of LGAT sensors. We do some laboratory tests by using some simple setups. We use this Transium 90 source to deliver 2 mega electron volt electrons. And then we got these studies in terms of time resolution as a function of the collected charge. And we can see that at high bias voltage, all the sensors satisfied the EGTD requirements. And also we have made many test beam campaigns, mainly at CERN, at the CERN SPS, using 120 giga electron volt pion beam, and also using 5 giga electron volt electron beam at DAISY. And we can see that in all the setups we used, the heat efficiency was of the data collection was 100%, as we can see in this gap in this pad here. And these are the most recent results that we got by analyzing data collected in 2018, 2019. We can see the time resolution as a function of the collected charge, and we can see that the EGTD requirements are set here at 70 picoseconds at the end of the lifetime of the detector as a function of the minimum collected charge required, which is 4 femtocoulomb. We can see that all the sensors that we tested from CNM and HPK satisfy the EGTD requirements. And here, finally, I presented the EGTD physics enhancement. We can see that in terms of the pileup jet rejection, we have an increase by a factor of 1.4 if we compare the ITK only, which is in black here, to the ITK plus the EGTD in red. And also we have some results here in terms of the lepton isolation efficiency. We have an increase of up to 25% by, again, comparing the black histograms from ITK only to the red histograms to the ITK plus EGTD. I think, yeah, that was it for my poster. And here we have a summary. I hope I wasn't running out of time.
No, you're perfect. Thanks a lot, Hassnae. So we have time for questions as well. So please ask questions if you have any. Let me start with one. When you talked about the improved performance that you get from it in terms of de-identification or in terms of lepton isolation, how does that work? What is the feature that you are that enables you to get this better performance? Is it the linking in with the rest of the tracking system, or what is it you somehow gain from it?
Yeah, of course, this is done by simulation only, and we have here a data set from the Z2EE, E+, E-, and yes, this is how it's done. So we compared here from the improvement of the tracks only from the ITK, and here we combined it to the EGTD and of course we can see that the EGTD helps to provide better track to vertex association.
Okay, thank you very much. Any other questions for Hassnae? It seems not. So thank you very much. Great to see the short presentation here as well. Again, if you have any questions later, you can ask them online. So back to you, Martha.
Okay, thank you, and congratulations again.
Thank you very much.
In our second place, we have Francesca Cavallari with a poster about HEPscape, an escape room about high energy physics.
Hi Marta, thank you very much for this award. I'm very proud of our project. So I'm going to present the slides. Okay, I hope you can see the slides.
Yes, if you can just get them to full screen would be great.
Yes, okay.
Yeah, we're there. Go ahead.
I'm going to present HEPscape. It is an escape room about high energy physics that we have developed in my group, that is the CMS INFN Roma group. I don't know if all of you are familiar with escape rooms. Escape rooms are like a treasure hunt, but in a closed room. The clues are hidden in a room, and usually the room has a decoration with a theme of history or some mystery or so. And all the clues unblock one by one the next level of the game, and usually there is a moderator that guides the solution of the puzzles. This is very popular among teenagers and also as among team workers, because it's considered a fun team building exercise. It has been exploited as well for outreach purposes, and there is a link in my presentation here in yellow, where you can look at a few papers, especially in the US, where this has been exploited. The message that the visitors get is that science is fun and they discover a new topic. So we have developed HEPscape, our escape room, and presented it at two science festivals. One first at the European Researchers' Night in Rome in October 2021, and then at the Science Festival in Genova, that is the largest science festival in Italy. And we have had more than 1,000 visitors. The escape room can be installed both indoor and outdoor in a gazebo. So in Rome, we were in a gazebo, while in Genova, we were given a nice room, and so we installed it indoor. The visitors have the impression of entering one of the LHC experimental caverns, and they are given a helmet, as you can see in this photo here, and they enter the LHC underground. Of course, they are not really going underground, but we make use of projectors on three sides of the room, and we project the movie of the lift going underground in the LHC pit, courtesy of the CERN superconducting magnet visitor point, as you can see in this video. Then we play some games. And we make use of light projectors to drive the attention of the visitors to the various clues, which usually are closed in a lock. In the room, there are also some posters that you can see here, for example, with the chemical elements or with the constituents of matter, and they are used to solve the puzzles. Just to tell you that we go as far as telling what is a muon and that the Higgs boson may decay in CMS, giving 4 muons, like in this beautiful event that you see here. Sorry, we have many games, and we have 2 game sets that are adapted to the age group of the visitors, and so everybody can have a fun experience. If we have younger visitors only, we do the younger visitor game. If we have a mixed group, we do the adult game, and we ask the kids to do the simple part of the game. So, for example, one of the games is the CMS puzzle, where they have to put the pieces in place. This is another photo of the kids' game, where they have to find up and down quarks here to make up a proton, and there are some crossword puzzles and so on. Ideally, the number of visitors would be less than 10, but in Genova we were asked to allow up to 30 visitors in order to have a full class. So during the game, we also give to the visitors a badge, where at the back of the badge they can find links for more information about high energy physics. And at the exit, we have an Instagram photo booth that you can see in this photo here. And we also ask to complete a satisfaction test with 2 questions, the age group and the vote from 1 to 5. And here is the result of the satisfaction test. We had the first days in Genova, mostly school groups. And as you can see, we got a good vote in general, both for younger kids that are here in brown and for teenagers that are here in light orange. While, of course, in the school groups, there were some teenagers that were not really very happy to be dragged around by their teacher in the city. So you can see this little dislike column here. The next days, we had mixed groups, mostly families with kids interested in science, but also groups of friends, and they all liked it very much because they were more interested and motivated from in the first place. So in total, we got a score of 4.4, so we're quite happy of this result. At the end of the escape room, we project the video of the discovery of the Higgs boson, as you can see in this video here. And then there is a discussion session with us, with the 2 moderators, with the physicists that are there. And in conclusion, the ESCAPE exploits the concept of escape room to explain science in a fun way. It can be built in 1 hour and transported to different sites. And the games can be adapted to the age group that of the visitors. And in principle, it can be duplicated. The content can be adapted to other experiments, other environments, and it can be translated into different languages. Thank you for your attention.
Thank you very much. This is amazing. You know, it really is. Martha, you have a question yourself, I can see.
Yes, thank you for the presentation and the poster. I like this outreach concept. My question is about diversity. Like, I imagine that, you know, you might get groups of people or parents that take their children that are already kind of interested in this kind of thing, or high performing schools. So do you monitor the diversity characteristics of people that attend? And also, do you do anything to try and attract people from traditionally minority groups within physics?
So the festival in Genova was really well organized, and it's really the largest festival in Italy. And so they reserve essentially the first 2 days to the school groups. In Italy, there is no highly performing class. Usually the classes are mixed with the highly performing students helping the ones who have more difficulties. So the classes are always mixed in this sense. Okay, while in the last 3 days of the festivals, it's individual groups who voluntarily come to the festival. So it's on reservation. So you really have to, be motivated to come to the science festival, I believe. Anyway, the festival was really nice and had many sites around the city. So people were coming to visit us and then going to other sites. It was really nice. We had among the moderators many girls, so we also this helped, I think, to pass the message that also young girls can study STEM and be successful and do interesting careers in science.
Thank you, Francesca. Can I ask how it is documented? You talk about at the end how it can be duplicated, how it can be adapted, and so on. So what kind of documentation do you have of the whole thing?
Yes, okay, if you want to duplicate it, we can give you all the films that we have and give you all the technical details of what you need to put up the escape room. We are going to write a paper about it, so we will write down all the documentation, and there are documentations how to build it and how to reset it after one group of visitors. So
okay, thank you very much.
Quite well documented, yes.
Good. I don't see any other questions, so I think also in the interest of time that we should move on to the final presentation. Martha.
Thank you.
And thanks
Thank
again,
you,
Francesca.
and congratulations. So for our third place poster prize, it is my pleasure to introduce Louis Dong with the measurements of the R value at best 3.
Okay, thank you very much. So I'm very glad to show you with your results from best 3 about the R value measurement. So can I start?
Yes, please go ahead.
Okay, thank you. Oh, sorry. What's the problem with this one? Okay, sorry. It's my pleasure to present the measurement of the R value at BS3. And the R value is one of the most important quantities in particle physics. It is defined as a cross-section of the hadronic process over the cross-section of mu process, as shown in this plot. R value also contribute to other important quantities like the rolling coupling constant of the QED theory. The level formula shows the relation of the R value with delta alpha. Red table shows the contribution from different sources. The hadronic process, as marked in red, contribute to the largest uncertainty. R value also contribute to the anomalous magnetic moment of mu, G-2 or A mu. This formula shows the relation of R value and A mu. Red table shows the contribution from different sources. Again, the hadronic process contribute to the largest uncertainty in the standard model calculation. The duration of the experiment and the standard model prediction is currently around 4.2 sigma, which hint there is new physics beyond standard model. To improve the precision of standard model prediction, it's important to measure the precise R value. We do the measurement at a base 3. Here shows the base 3 detector. And it's an electron positron collider working at a central mass energy between 2 GeV to 4.95 GeV. Those labels here show the performance of base 3 detector. In experiment, the R value is determined with this formula. The number of the observed hadronic events subtract the background and then divided by the luminosity, efficiency, correction factor, and mu cross section. The table here shows the data used in this presentation from 2.2 GeV to 3.67 GeV. And the diagram here shows the event selection. The main goal of the selection is try to reject QED background. The most important part in this work is the color simulation, as it will provide the efficiency, correction factor, and so on. And the simulation is the largest systematic uncertainty source. So we use Lambda L model to do the simulation. It is developed from JSET for low energy experiment. The right figure shows how Lambda L model works. And in the generator, we also consider the initial state radiation and the vacuum polarization effects. And the Feynman diagrams here shows the ISR and the VP effect. To further validate our simulation, we implement another generator, hybrid. In principle, R value is determined by the sum of the hadronic processes. Red table shows a comparison of the coefficient from R value and the sum of exclusive hadronic processes. Below 2 GeV, they agree well. Above 2 GeV, the exclusive hadronic process is incomplete. And in the hybrid generator, for the well-known processes, we use Convex and Focara to do the simulation. And for the unknown processes, we use Lambda L model. Red figure shows the contribution to R value from different exclusive hadronic processes. The difference between the hybrid generator and the pure Lambda L model is less than 2.3%. Here shows a comparison between data and monocolor at 3.4 GeV. For those figures, data are well reproduced by the tuned Lambda L monocolor. And here goes to the systematic uncertainty. The uncertainty is estimated based on the formula used to extract R value. Most of the uncertainty are less than 1%. The largest contribution is from the simulation, which is checked by the hybrid generator, less than 2.3%. And here is a summary. B3 has done a lot of work in the R measurement. We have 2 generators and both of them can describe data well. We have obtained R value in 2.2 and 3.7 GeV. The result is shown in this figure. Red dots are from B3 results. The accuracy of our result is better than 3%. And the paper has been submitted to PIL. And here is only part result from B3. And the whole R value program will cover a wider energy range from 2 GeV to 4.9 GeV. Hope it will come soon. Thank you for your listening.
Thank you very much, Leo. Questions, please. Martha.
Hi, thank you. So on your first slide about the motivation, my question, I think you mentioned it a bit. It's about the contribution of this to the measurement of G-2. Now, can you comment, like, is the R value the leading systematic uncertainty for G-2? And if so, do you expect this to increase, to improve, and therefore help the G-2 measurement?
In the white paper of the G-2, it has listed the contribution from the hadronic process. Here the uncertainty is 40. And here you can see in the total uncertainty 43, which mainly contribute from this. And I'm not sure how large contribution from the our energy region, because the contribution is mainly from the lower energy below 2 GeV. So improve the measurement of the R value will improve this, will reduce this uncertainty.
Okay.
Okay. The leading systematic for you is the simulation.
Yes.
Are there any ideas about how one could improve on that?
Currently, we try to tune the parameters in the Monte Carlo, in the London error model. Try to make the better consistency between data and the Monte Carlo.
Mm.
And
there's a lot of developments happening at the moment also in within the Pythia collaboration on improving the treatment of radiation in general, mainly of gluon radiation, but that's work that's moving on to QED radiation as well. So it's an area where I think further collaboration could be very interesting to improve on this, you know,
yes.
Really, really important measurement. Okay, are there any other questions? I don't see any, so let's say thank you very much again for the presentation. Thanks to all the prize winners. This was amazing to see these posters, and thanks for volunteering to give presentations also on a really short notice. I believe that we have half an hour's break now. I think it would be great also if these presentations could go on the agenda, so just as a message to the Manchester people, and be listed who actually won the poster prizes. But otherwise, we'll start again in half an hour.
Thanks very much, Ulrich, and thanks to you for chairing, and also from my side, congratulations to all the poster winners. On the presentations on Indico, absolutely. I should add, I have deliberately asked them not to upload their presentations before the prize ceremony, not to give something away, but yes, we do hope to have a full set of slides on Indico indeed. All right, so yeah, let's have a break for half an hour.